My name is John Cazes. I'm the Director of High Performance Computing here at TACC. And I gave this update, I think about 2 years ago. I missed last year. And so we've had a bit of change since then. So first, for those of you who aren't familiar with TACC, since you didn't get to come, TACC is a computing center primarily funded by NSF that supports national researchers across the country, primarily NSF researchers, although we do support researchers from NASA, NIH, and a few DOE researchers. And in this picture here, you sort of see the beginnings of clusters, Grindle, and where we've evolved to, at least here at TACC with FRONTERA. And I'll go into a little more detail about FRONTERA a little further on. And so this is sort of TACC at a glance. We have 185 staff. We have 12 megawatts of power, and hopefully soon we'll be building more. We have 3 buildings, 2 office buildings and 1 machine room. We have a Viz Lab here. We are on a remote campus at UT, and we have a large Viz Lab on the main campus to serve faculty and researchers down there. We offer billions of compute hours per year. We have probably 15,000 users we've supported and maybe 3,000 to 4,000 projects. And if you count our portal users, many, many, many more. And so we've grown quite a bit over the past 15 years that I've been here. And now we provide a lot of computing resources and support. And so here's just a quick look of our ecosystem, and I'll focus in detail on FRONTERA and Stampede 2, but we also have systems for Texas users, Lone Star 5. We have systems concentrating on GPUs for machine learning and mostly molecular dynamics. It's Longhorn. We are partners with Indiana on our cloud system, Jetstream, half here, half in Indiana. We have a small GPU-focused system, Maverick 2, which sort of the unique thing about Maverick 2 is it's in mineral oil. We also have a 30 petabyte archive and 20 petabytes of spinning disk. And one of the other things we have that is an advantage and also the bane of our existence is Stockyard, our shared Lustre file system that touches every system here. It makes it incredibly convenient for our users, but when there's a problem with Stockyard and our /work directory, it's also a problem for every system we have. Okay, so before I go on into details about our hardware, which is almost predominantly Intel, I want to mention just a little bit about the coronavirus, since that's why we're doing this all over Zoom and virtually. And since March, we've been part of the COVID-19 HPC Consortium, and we are supporting in several different ways, as I'm sure all of the other centers who will do site updates in this section are too. And it sort of started with epidemiology. We have an epidemiology researcher on campus who's worked with us quite a bit before. And as soon as it started getting out of hand, we had a partnership in which we spun up their research efforts and set up dashboards. And so we do regular updates with them on their applications and their data and for the dashboard. And then sort of the next step is we already supported several drug research projects. Well, now they're all focused sort of on drug development workflows to combat COVID. And this is primarily taking place on Stampede 2 and FRONTERA. And then finally, we have researchers modeling the virus directly. And so you see in these pictures, those are visualizations of the spike. A lot of the simulation to actually fully resolve the spike was done on FRONTERA here with Romy Amero's group out of UCSD. And there's a little blurb over here on the right, and I'm going to emphasize that. So we got up and running in March as part of this consortium, and we pretty much had everybody going by April, May at the latest. And part of the reason was because they've been running here for quite a while, and so they were comfortable with our systems and our people, and we were able to get up and going very quickly. And then thanks to NSF, we were able to provide allocation and resources in a very short time. So our second largest system used to be our premier system, Stampede 2. And this is what I reported on a couple of years ago. In 2018, Stampede 2 was a little under a year old, and it's composed of KNLs and Skylake nodes, 4,200 KNL nodes, a little over 1,700 Skylake nodes. And it's all connected with Intel's OmniPath. So this is our workhorse system. This system supports over 1,000 projects via NSF and the XCEED program and over 5,000 users. And let me tell you, they run the gamut from very novice users to very experienced users. And this machine will be in production for at least a couple more years. And so Frontera is now our flagship system, which we installed last fall. So we're just hitting about a year of service. And so this is over 8,000 nodes of Cascade Lake, 2 28-core chips per node. So they're the top end, the platinum SKU for Cascade Lake. We also have, and I don't have it on here, but we have 90 GPU nodes where we have NVIDIA Quadro RTX 5000s. And here we see a lot of machine learning and a little bit of MD. And these nodes are also a little bit different because they're in the oil. And this is all connected with Mellanox HDR InfiniBand, which we've struggled with over the past year, but I think we've finally got it running fairly efficiently. So the whole system is about 38 petaflops. Each node is about 4 teraflops. And so just a little bit more information about Frontera. When we're running at peak power, which we probably never do unless we're running HPL, it can consume about 6 megawatts. And our whole center here on this campus, I think, is about 10 megawatts peak load. So it has its own. We built a new water cooling facility for Frontera, a new powerhouse. We also, I don't have it on here, but we have a special cooling facility where we have a huge tank where we basically cool water at night, fill the tank up, and during the day when electricity is at its most expensive, we turn off the chillers and we draw down from the tank. Also, we have a part for the oil immersion. All the GPU nodes are immersed in oil. So we save money there because it's much cheaper to cool using oil. We have solar and wind, I think, offsets in our power grid. So we make sure part of our power comes from solar and wind. And so the next system we have will probably be 3 times this power. And so we're also in the process of just getting a new substation built to supply us with the power. So Frontera is ranked number 8 in the world today. It was number 5 up until the most recent ISC, and then the Fujitsu system and a couple of other systems have pushed us down. We are the fastest Intel system, we're the highest ranked Dell system, and we have the highest ranked systems for US universities. So I guess sort of the unique features, I already alluded to one of these. We have these RTX nodes, which have quadros on them, and they're all immersed in oil, but they're connected into the same network as all the regular Cascade Lake nodes, and they're all in the same file systems. So it's basically just a different queue. Users can run on Cascade Lake, they can run on the RTX nodes. We also have Intel's Optane technology. These are NVDIMM nodes where basically we have NVDIMM memory, and right now we've got them configured so it's 2 terabytes of memory per node, and another 3.2 terabytes are configured as disk. On occasion, we can reconfigure this so there's 6 terabytes of memory per node, and we do so upon request. And so the idea here is if you have a problem that has really high memory requirements, but you still can't, say, use MPI to distribute it across nodes, or maybe you have some sort of database application that needs a lot of memory and fast access, you can run it here. And actually, we're also using these nodes to do some DAOS testing currently. So here's a look of the science we support, and this is just FRONTERA. It looks a bit different for Stampede 2. FRONTERA is a more restricted system, whereas Stampede 2 is a system for everyone, sort of a capacity system. FRONTERA is a capability system. And so the users on FRONTERA, there are fewer projects and they're more experienced users running at a larger scale. And we see that most of our allocation here goes towards astrophysics and fluid flows. And then for materials research and biophysics, that's mostly molecular dynamics. And it skews a little bit differently on Stampede 2. On Stampede 2, it's much smaller for the astrophysics and the fluid flow, and it's predominantly molecular dynamics and weather, climate. So one of the unique things we do in FRONTERA, we started doing this last year, is we have something called Texascale days. And so what we do for a little under a week, we will dedicate the whole system to large runs, where we'll have 1 or 2 projects running on either half the system or the whole system. And they run up to 7,900 nodes. Now, we only do this after a maintenance because since for a maintenance, we have to drain the nodes anyway, we take that opportunity that we're starting fresh to basically start these large scale jobs. If we tried to do this during a regular production run, we would have a time in which the system would not be well utilized because we'd have to be draining the whole system to start these jobs. And the first requirement we have for the projects that run at this scale is they must have run on 2K nodes, basically. Our large queue supports up to 2K nodes, and projects who have demonstrated that they can run at 2K nodes successfully without causing issues with the file system or issues on the network, and they can run efficiently, we basically offer this to them when we do Texascale days. And we're probably on track to do 3 or 4 a year. Our next one will probably be in December. And as part of Texascale days, what we do is we give each project 24 hours with the system either dedicated to them or half the system. And we work with them to get their code up and running, because usually this is the first time they've ever tried this. And so it might take us maybe half an hour to get things running smoothly, and then they get to run for the rest of the day. And so for the past 3 exascales, we've supported over 14 projects. And one of the ways we work with them is we have special Slack channels set up, because it's really difficult to do this by email or by conference call. But through Slack, it works pretty well, because you can speak to the whole group who's running the code, the developers, and you can include the admins. And so sometimes when we start these codes up, we find out that we have hardware issues, and we have to ask them to pause, or we reset switches or reboot nodes. And then sometimes they notice things and they let us know, and we can go investigate. And so this has been a really valuable activity. It helps us shake out the hardware and run at the scale we've designed the system for. And the researchers get to do projects and attack goals that they might not be able to on a regular day. And so now I'm just going to mention a few of the projects here. So one of the largest is Paul Woodward's hydro project. He's doing stellar modeling, convection boundaries in a large star. And on our first Texascale, he was able to run basically the whole weekend, almost 80 hours straight, over 7,300 nodes. What's really impressive is this 588 gigaflops per node. That's about 13 or 14% of peak. That's really high for an application to sustain. And he has some great visualizations. Another project, Dan Bedoni, he looks at hypersonic flow, and it's nice in that, unlike Paul, they actually have physical experiments that they can compare to from their simulations. And his code scaled pretty well, really well, to 2,000 nodes, and then fairly well to 4,000 nodes. And notice they were only using 2 ranks per node. And so that helps too if you can run in a hybrid mode, because that's only 8,000 ranks total. And then, and I think this is the last one because I'm running out of time already. Alexei Aksimentiev, he's running NAMD. He's also run up to the full system scale. And for the problem they were using, it scaled really well up to about 4,000 nodes, and then the scaling dropped off. And so they're looking at coming up with a larger system that they want to model that they can run on the full scale. Oh, whoops, one more. Greg Voth's group at University of Chicago. I don't think it says it on here, but I'm pretty sure they're running LAMPs. And so they're also looking at things like HIV, and they've run up to about half the size of the system. And they're looking at what problems they can analyze when they run at full scale. And I am out of time, and I am over, and I apologize for being 3 minutes over. That's my email address if you have any questions, and if I can find the Slack, I'll answer them there.